finishing chapter 16, no matter what it takes. I already took one of the mechanisms you're supposed to learn, and it's like, you know what, I didn't learn that till grad school, so no, it's gone. Or at least I wasn't required to memorize it until grad school, so we're not gonna go over it hardcore. You guys can have the mechanism and look at it if you're interested. Maybe we'll start, that would be nice if we could start chapter 17 and just get like nomenclature and like all the stuff that we do before we actually start doing reactions. Nomenclature, physical properties, those things. I hope we can get that done today. Regardless, I am paring down the slides a lot because, well, I mean, to be fair, I didn't actually start with slide decks that were like that someone had gone through in an appropriate amount of time. I started with directly from the publisher, and I cut out like a third to half of the slides just from the beginning before I even started teaching, even last year. And yeah, so I'm cutting slides in a specific way so that hopefully what we cover, we're going to cover well still. I don't want to like rush through the rest of the chapters, because if I don't do some serious editing of the slides, we're just going to feel like we're really rushing through all the rest of the content. And that's the worst way to learn. So what we learn, we're going to learn well. That's my goal. And the exam is going to, so Friday we're going to do all of carboxylic acids. Yeah, it's gonna be fine. Your exam will include carboxylic acid things. Yeah, your exam will include some carboxylic acid things. Obviously not a ton, because we spent nearly 2 entire weeks on chapter 16, so like your exam is going to be mostly chapter 16. In fact, your exam is going to be eerily similar probably to the first practice exam that I posted, because I thought when I posted that it was going to be, that was like the first third of the class, and then, you know, the second third of the class or something. No, not exactly, but that's fine. So that first practice exam is chapter 15 and only 15, 16. So there's only a little bit with carboxylic acids before you go into carboxylic acid derivatives. That'll be on there. Then we're going to do carboxylic acid derivatives as quickly as possible. Do chapter 19, I will pare down a lot of that, and then we're going to get to dienes and benzene with 2 weeks left. So I think this bit is not going to be overly rushed. I think this is actually, I think that chapter 19 is going to be the most difficult. Get rid of more and more stuff as we go, and then just, you know, if we don't cover it in class, I'm not going to test you on it. And yeah, this is a question mark, because I don't know if we'll get this far, and I've completely cut out all mention of biochemistry things, because you know what, that's fine. I mean, if you take biochemistry, you'll take biochemistry, and they'll pretend that your alcohols look like this, and everybody will be okay with that, because, okay, it's easier to draw and stuff. So that'll be fine. Honestly, there's not a ton in the biochem things that are, I think, that interesting to hit anyway. So that's my current plan. I was going to try and edit. I made it on here, and then I edited the one I have right next to it. Wait, where's? And then I changed this, which I hated in this format anyway. And then I remembered when I tried to put this on Canvas that I had to redo the entire thing in Microsoft Word in order to get it on Canvas the first time, so I just deleted your initial course schedule from Canvas and instead uploaded this. whole thing. Yeah. So you have that at the top of, let me make sure you have that. I think it's at the top of your syllabus. I'm pretty sure I just put like a link to it. So, syllabus link. Yeah, at the very top of your Canvas, I put that. So there's your, as of now, course schedule. I put a link up there, and then if you scroll all the way down to where it said tentative course schedule. Oh, well, it used to. Or I skipped it. It's hard to see. Oh, there it is. Where it says course, where it used to say course calendar, I put another link to the same thing. So, if you want it in list form, you still have it in list form. Oops. Stop reading all of my emails up there. Why am I doing this to myself? If you want this in like the list form, wow, it's really difficult to maneuver a mouse backwards. You still have it in the list. This is the same format that it is on Canvas. It just, Canvas doesn't play well with this. So, that's the current plan. I'm going to be spending a lot of time with your slides to decide what we can cut out and hopefully cover a solid amount that still counts as organic chemistry too. I think we're going to be fine. But the biggest thing is I don't want to just like sprint through the rest of the semester because that's just not entirely useful. So, selective reduction. We can do selective reduction as in basically we want to reduce a ketone or aldehyde and we want to leave something else alone. So in this case, we're going to try and leave alone this double bond, or I guess selective reduction is really just picking one of them, right? Because you might have learned how to reduce double bonds before, but you didn't have, we hadn't talked about carboxylic acid, or carbonyls at all. So when you learned how to reduce double bonds, you weren't even thinking about having to leave an aldehyde or a carbonyl alone. So if you want to just reduce your aldehyde or ketone to an alcohol and leave a double bond alone, you're going to use LaLH4. LAH. That's going to leave a double bond alone. It's also, you know, aggressive with water, but you win some, you lose some. Selective reduction of just the carbon-carbon double bond and leaving this alone is going to be done with rhodium, and it says it's performed using rhodium on powdered charcoal as a catalyst. I don't really know why. I assume just because like any solid can only get granules so small, you know, and rhodium's really expensive, so it's probably some combination of however much you're really going to need to weigh out is either like infinitely small if you just have like rhodium, like just some rhodium, or it's just sort of, if it's spread out over particles of carbon so that like the center of all of these granules aren't expensive rhodium that isn't actually really going to disperse into your reaction mixture and participate in catalysis, then you're saving a lot of money, and you know, so I don't know. I mean, rhodium on powdered charcoal is probably one of the cheaper rhodium catalysts you can get, because powdered charcoal is like nothing. Usually you've got all sorts of ligands in there that need things. So, reductive amination. Reductive animation, we've already kind of talked about this a little bit, but we talked about how you can react a carbonyl with an amine. And when we do that, we end up, instead of just adding the nitrogen and just having an OH and an N, we end up kicking off the OH. We have to do this in acid, right? Because OH is not a good leaving group. So we kick off the OH by turning it into water, and we double bond with the amine. If you want to get rid of this afterwards, this amine intermediate, I mean, they're calling it an intermediate because the goal of this reaction is to get to this, but like, it's just an amine. Then you can use H2 and nickel. God. You can use H2 and nickel to reduce that and turn that back into an amine. And you get this. So, nickel or another transition metal catalyst, because really if you stick palladium or platinum in most of those simple ones, like most of these simple ones that are just like H2 and nickel are like a reduction or something like that, if you stick any of the like more exciting metals in there, they'll also do it, but you know, nickel if you can. Palladium is X. And okay, reductive amination can also be carried out in a single step. So you can, this is the two-step, we make an amine, and then we reduce that, reduce it. You can also do this in one step if you use sodium borohydride, NABH3CN. So it's similar. Not sodium borohydride. NADH3CN, not NABH4. So similar to the other one where we have NABH4. This is going to be and boron, if you make that into a, if you actually do, does it make, I think you can make inorganic salt with boron. If you do, it ends up having a +3 charge, right? Like, it doesn't end up having a negative charge, it's not going to keep these. So, basically, that's kind of what you're going to have, get rid of there. You don't need to know exactly how this is set up, but, and then that, and that hanging out somewhere. Regardless, you can use that, and I just want you to know, this is a one-step way of turning this and this back into an amine, but putting them together. Amine, there we go. I should be saying amine and amine. But that's the thing you can do. Clemmensen reduction. Can I go back to this? Is this all right? Okay. It's just so shiny right up there. Clemmensen reduction. This is a type of reduction where you use zinc, mercury, and HCl. It's like a zinc and mercury. I bet that this is just like, there's a bunch of like ligands up in there that are just sort of holding all that together, and we just don't need to know that. But zinc and mercury kind of together in some sort of complex with HCl can produce an aldehyde or a ketone. And it reduces it all the way to a CH2 group. So instead of reducing this guy to an alcohol and having two of those, it gets rid of that oxygen completely. Gets rid of the double bond, gets rid of the oxygen. But weirdly enough, it's not reducing this alcohol. Oh, never mind. Yeah, no, I'm not entirely sure why it's not reducing that alcohol. So to reduce that. I swear I look at these and I just don't realize which things are gonna bother me. Yeah, it just doesn't. Oh, okay, I see. This isn't a two-step process. So you never actually form the alcohol in the process of reducing this. It just reduces it straight to the CH2. Usually with some shenanigans with the metals where in order to draw the mechanism, like you have to draw it conveniently to make a nice little circle because in the end you have to spit out the thing you started with because it's a catalyst and it's all over the place and a lot of metal stuff. I don't like metals. So that's something you need to know. If you want to leave an alcohol alone, you can do that as long as you're trying to get rid of the ketone or aldehyde completely. Wolff-Kishner reduction. We have a mechanism on this. It's in your slides. You don't have to know this. You have to know Wolff-Kishner reduction. You don't have to know the mechanism for this guy. Deal? So basically, this is reduction of the CO group of an aldehyde or ketone to a CH2 group, all the way down to that. And you're going to take hydrazine, which is like, it's not like the safest thing to work with, but I mean, also we're talking about LAH and we talked about lithium organic, organolithium compounds. So like, this is much better than that. At least, I want to say, because I don't remember the A6. I think it's fine. It's fine enough you can heat it up with KOH, and you're going to heat this up a lot. Like, you specifically pick your solvent so that it's a high boiling solvent, so you can get this a ton of heat. And that's going to just completely reduce this guy down to there. Basically what happens is these nitrogens, they start with a double bond right here, and you end up kicking off N2 gas. Actually, here. So you kind of do like there's a bunch of steps, and you get this guy, and who cares how that happens, you get this, and that's like, oh, this is some weird ways to do it, but we end up with an imine. And then you deprotonate it. Well, an imine, I mean, if you just look at this by itself, it's an imine. It's a hydrazone because, you know, the thing bonded to the nitrogen is another nitrogen and not a carbon, but whatever. It looks like an imine. Looks like organic chemistry. You deprotonate that, and you start forming bonds between the nitrogens, and once you start doing that, it's all over because one of the strongest, I mean, we use, okay, yeah. You do that, and the nitrogens are like, I would really like to just do my own thing, and we do a bunch of proton transfers, like a bunch of them, and then finally, we're like, hey, you know what? What if we just like peace out? You can do your own thing, and we're just gonna go triple bond nitrogen to nitrogen and be nitrogen gas, and that's cool with us. And nitrogen gas is very stable, right? Because we do a lot of chemistry under nitrogen gas. I mean, depending on how rich your lab is and what you're doing specifically, there are a couple things you can't, there are definitely some things you can't do under nitrogen gas, so you have to do them under argon. If your lab has enough money, you'll just sort of have argon tanks and you'll do stuff under argon and whatever. If you do like everything under Schlinkline and glove boxes, you might do nitrogen when you can, but that is the driver of this reaction. Because once you get to here, we don't have, like, you can't go back. Yeah? All right. Don't need to know that mechanism. So, H2PT, what's that going to turn this guy into?
An alcohol.
Yeah. What about NADH4 with this? Is it going to turn this into what does it turn this into? And does it touch this? Oh, I wanted the picture up there, not the answer, but what do you give this? So that guy's also reduced to an alcohol. Yes, NADH4 and LAH with aldehydes and ketones specifically are interchangeable, except LAH is more aggressive. We're gonna get to other things and they're not gonna be interchangeable anymore, so don't equate them in your head just yet, or else you'll have to undo that. But this one is a primary alcohol and this is a secondary alcohol, and they keep acting like that's a whole different reaction, but like, who cares? The two things that we have bonded to it are still bonded to it, and the two things we have bonded to it are still bonded to it. So like, I don't know, reduction reactions, let's see. If you do zinc, mercury, complex things, is it going to, what's it going to reduce? There's an alcohol, an ether, and an aldehyde. What gets reduced? Aldehyde. Anything else? No, right? That's like the whole thing with that. This one is Wolff-Kishner, and there's nothing there to see if we need to leave it alone. So, okay, we just turn that into a CH2, and there we go. It looks exactly the same. I mean, the rest of the complicated structure looks exactly the same, is where I was going with that, sorry. It looks like a really complicated question because it's a weird multi-ringed structure, but you just reduce that and you're done. Reactions with alpha carbon, racemization. So, I wish these slides had not been lost to the ether.